It is now week 6 of distance learning with your teacher, Mrs. Ruvalcada. Thank you guys so much for looking at my recorded lesson. Now, onto the agenda, we will do our usual reminders, the assignment overview, and also our interactive lesson where you guys will be typing in your answers as you watch this lesson video. So the reminders will be to always take your attendance every single day. Go to my flex hours if you have any questions about this lesson. Mondays are reserved for periods 1, 3, and 5, and Tuesdays for periods 4 and 6. Please join my live session the very next day. That gives you guys a chance to ask for any clarifying questions about the assignment, the parts that you don't quite understand. And also, please turn in your assignment before midnight by Sunday, 11:59 p.m. Now, your assignment for this week should look like this. We are doing chapter 5.3, acids, bases, and salts. Answer this catalyst question in the box. How can you tell if a solution is an acid? How can you tell if a solution is a base? Think about that. Put in your answer. Pause this video if you have to, and then move on. On to the next box for the objective for this week. Students will be able to compare and contrast 3 acid-base theories by completing a table and answering review questions. Now put this in the standard box. HSPS 1-2, explanation for simple chemical reactions based on chemical properties. Make sure you put this in the standard box. Now, let's talk about the common traits of acids and bases. Acids normally taste sour, and they are highly reactive with metals. Bases, on the other hand, have a bitter taste to them and also has that slippery soap-like feel. Another way to tell numerically if this is an acid or a base will be on the pH scale. Anything less than a 7 is acid, this side over here. Anything more than a 7 is a base, this side over here, the right side of the scale. 7 is neutral. Now, why are we studying acid-base reactions? This trails after your lesson on solubility and also calculating concentrations. We study acid-base reactions so we can see which compounds can dissolve in water. And also there's a lot of real-life applications in terms of the concentrations of acids and bases, how it affects the human body, and also for manufacturing goods for consumption. Now, in terms of the human body, there are these conditions known as acidosis, which means the pH level is below 7.4, and alkalosis, which is basic, more than 7.4. And being in the state of acidosis and alkalosis can have negative effects of your body. Your body needs to have the right specific amounts of pH so that the chemical reactions in your body can function, so that your bodies will be in tip-top healthy shape. Now let's compare the 3 types of acid-base theories. The first one is the Arrhenius acid-base theory. The second one, Bronsted-Lowry acid-base theory. And the third one, Lewis acid-base theory. Lewis sounds familiar, doesn't it? Like our Lewis structures. Okay, moving on to Arrhenius. He is the original guy that proposed acids and bases from around circa 1884 to 1887. One textbook says 1884, the other one says 1887, so I went ahead and put in both dates around that time. And how he describes acids is based on the hydrogen ion and hydroxide ion concentrations. And hydrogen ions are these hydrogen, the symbols. Remember, the symbol for hydrogen is a capital H. And since it's an ion, it lost an electron. So that's why it is a positive charge. And these brackets indicate that it is in concentration. Now for hydroxide, it's a polyatomic ion and it is a negative ion. Oxygen and hydrogen covalently bonded, and again, the brackets represent concentrations. So he described acids and bases based on how much hydrogen ions there are or hydroxide ions in the solution. For example, an areneous acid, it's any substance that increases the hydrogen ion concentration in an aqueous solution. So let's take a look at this example here. We have hydrochloric acid, HCl, mix that in water, okay, like what happens here in this picture, this diagram. When you mix it in water, they completely dissociate, resulting in these hydrogen ions in the solution. And the presence of the hydrogen ions in the solution indicates it's an acid according to Arrhenius. For the Arrhenius base, remember, this one involves hydroxide ions, OH, and yes, you can guess that with an Arrhenius base, it's any substance that increases the hydroxide ion in the solution. So sodium hydroxide, a strong base that will dissociate completely when you mix it in water, will result in lots of hydroxide ions here. Now the Bronsted-Lowry acid base. That one is a little bit different and a little bit more refined, and it is proposed by Johannes Nicholas Bronsted and also Thomas Martin Lowry at around 1923, where they said that to describe an acid and a base, it depends on substances that gain or lose hydrogen ions, just hydrogen ions, okay, not hydroxides, because it turns out that there are some bases that don't have the hydroxide. It doesn't have an OH. So it is actually based on whether hydrogen ions are gained or lost. For example, and let's take a look at this cute little picture here with this lemon throwing hydrogen ions in this glass of milk. So we can guess that this lemon represents acid and the milk represents base. A Bronsted-Lowry acid donates a hydrogen ion, and it is also known as a proton, and let me show you why. Okay, it's a proton because we know that a hydrogen has one proton in the nucleus. Okay, and here is an energy level with one electron, that's a negative. And when the electron leaves this atom, it becomes a hydrogen ion. When that electron leaves, all that's left is just the proton with no electrons. So it's just a proton. That's why scientists call hydrogen ions as plain protons, okay? And here is an example of a chemical reaction. We have our strong acid, hydrochloric acid, and mixed with H2O, water, to yield chloride ions and this hydronium ion, 3 hydrogens and 1 oxygen. Okay, and let's take a look at what's going on in this chemical reaction. If I can get my little pen to work again. Okay, there you go. So it looks like this hydrogen ion, or rather this hydrogen atom, is leaving this chloride. So this hydrogen will give an electron. So now it's just an ion that will now join this water molecule, resulting in this ion called a hydronium ion. Hydronium ions, protonated water molecules, as in it received a proton. It's no longer H2O, it's now H3O with a positive charge. So this one is the acid because it donated that hydrogen onto this water molecule. And the opposite of that, the Bronsted-Lowry base, that one accepts the hydrogen ion, also known as the proton, which is what is happening to this poor milk here. It is accepting those protons from that lemon. So what's going on in this the sample chemical equation. And let me see, I still need my pen here. So what's going on here? We have this hydrogen atom that will break off of this water and go to this compound, this ammonium compound. Now this compound received this hydrogen forming NH4+. Therefore, it is the base, because the bases in Bronsted-Lowry are the ones that accept hydrogens. And then the next one is the Lewis acid base. Lewis acid base, right here, Gilbert Lewis, the father of covalent bonds, also at around 1923. So instead of talking about hydrogens, protons, and also hydroxides, this time he describes acids and bases as the ones that will receive electrons or give electrons. It's based on the transfer of electrons. So a Lewis acid will accept an electron pair. A Lewis base will donate an electron pair. And here is a generic example. We've got the Lewis base with the electron pairs giving away those electron pairs. The one that accepts those electron pairs are the acids. Now, can you guess which is which for this one in the reactants? Well, this one has the electron pair, and later on it ends up as this compound here. So this electron pair will be donated to this compound here, the BF3. Therefore, the NH3 is the Lewis base, and the BF3 is the Lewis acid. Now, did you fill in this table? Okay, so for this table, you are going to describe what the acids are for each of these three theories and what the bases are for these three theories. So you're going to want to have to stop this video and go back and review. Okay? All right, now this is a table of the common acids here. Let's take a look at what's going on here. Now, the question for this is, what do acids have in common that differ from bases? Take a look over here. We start with the anions and the corresponding acids that form from that. What do you notice the same about all of these guys here with these acids? What types of particles did they originate from? Think about that. And then the next question that you're going to have to answer for the common bases. What do bases have in common that differ from acids? So take a look over here. We've got these particles. Notice that these are cations, and the corresponding bases. Notice what they look like afterwards. And remember, not all of them have a hydroxide, like this guy here. Okay? And before we move on to the next part of this chapter, I want you to review the three types of acid-base theories, fill in the table, and answer all the acid-base questions in the assignment. And if you were able to compare and contrast the three acid-base theories, then you have satisfied this objective for this part of the lesson.